I was, of course, there to do the science. So for my project, we did a lot of work in Terra Nova Bay, which is kind of like in the second or the third week from when we arrived. And you first prepare your moorings, and I'm going to tell you how we're going to do this. So what is a mooring? So here on the right side, you see a mooring. So you've got the little brown disc at the bottom, which is a big weight, and we use old railway like wheels for that. We have a chain, and then on that we've got a long line, and on that long line we've got multiple instruments that measure the properties of the ocean. So like the currents or the salinity, the temperature. Some of them do oxygen. And yeah, so we program them to last 2 years. Preferably you pick your mooring up every year, because there is quite a big chance that you have an iceberg that wipes out your mooring. If that happens after 3 months and you pick it up, try to pick it up a year later, then you haven't lost that much data. But also instruments can corrode, or in that way water can come in. So you prefer to turn around your moorings every year. But we programmed them to last 2 years, because one of our moorings was covered, well, there was sea ice above it, and then you just can't get it. You can ask it to release, but it will get stuck under the sea ice, and then you lose all your data. So yeah, so that's the programming thing. And after that, we lay everything out on deck. So that's the left bottom picture. So those green things are acoustic releases, but they'll exactly do I'll tell on the next slide. Then our instruments, and then some floats. And then on the right picture in the middle, you see the big rail wheels that we used as weights at the bottom. So this is a mooring deployment. So we had it kind of already in, so you can see the floats and then the instruments, and then you drop the big weight, and then it literally just floats to the bottom, which is like really quite cool to see, because it kind of just gets dragged down. Cool. The year later, you come back and you want your mooring back. How do we do that? So remember those green things, those acoustic releases. We can talk to them. So we do that with an echo sounder, which we can see here at the right bottom. So we put that over the side and put it under, make sure that it's under the hull of the ship, and we let it chirp. Hopefully, if everything goes well, our acoustic releases hear our chirp, they chirp back, and we're talking to them. We then send a different chirp to say, could you please release? And then there's a little hook that releases, and then those floats that keep the mooring straight make it hopefully come up to the surface. When that happens, that's great news. So, but if it's still floating in the ocean, you still don't have your data. So you have then a big hook that has a rope on it, and we like throw it overboard. We try to like catch it on like one of the ropes or one of the big floats, and then we hold it in. And then we attach it to a winch, and we like get it on board, and that's when you're happy. And then your instruments come back up, and then you're extra happy. And then after that, you look at your data, and when you know that you've got your data, that's when you can really smile as a scientist, because it's quite hard for stuff to survive in the ocean. So this is a piece of metal that erodes. This is material that erodes easier than the metals from your instrument. But yeah, if an iceberg comes along and it kind of pulls the cable, for example, things can break. If you put stuff in the ocean, stuff breaks. So it's, it's quite a big operation to get your data. So this was something that was really exciting, but I do want to share some like other highlights with you. So I told you I made a little to-do list to keep myself busy for all those days that we didn't have to do any science. I did not have to do that. That list got thrown overboard because Antarctica gave me a lot of things to be super excited about. So one moment I want to highlight that was, I think, the thing I took away mostly, which was a katabatic wind event. So a katabatic wind event is when you have wind that kind of like rolls down the ice shelf It's really strong, very cold wind. It pushes all the sea ice away. That wind is so cold that the top layer of the ocean refreezes, and that's how sea ice is formed. And that's rough. It definitely doesn't look like this nice, beautiful ocean here. I don't have a picture of how the ocean looked like because I was lying on my cabin floor being seasick. But yeah, this is kind of the area that I study. I look at katabatic wind events and how the ocean responds to that. So I've been looking at satellite images on, to katabatic wind events and kind of trying to study them, and then actually being in there and feeling the scale and knowing actually what it does and like the waves it generates and like the freezing cold air that comes in. That was definitely something that was really special for me for this trip. Then the Ross Ice Shelf. So there we go. Then you can hear me. So we sailed all along the Ross Ice Shelf. And that's is like 600 kilometers, and it's called the barrier by like the first people that got to Antarctica. And that was spectacular. And then so we saw like weather systems in the distance, and we like sailed through weather systems while we're still just sailing past this block of ice that stretched hundreds of kilometers further south and still with an ocean beneath it. And just to realize that was just crazy. And then the other thing, so this is everything that's above the surface, but still, again, 90% of it is still below the surface. So it was taller than our boat. So that was really quite special. We got to go on land. I really hoped we would get on land. So this was at the Italian station. We had a stunning day. We saw more penguins, which, like they just brighten your day. And then this is at 2 a.m. So we got to experience like the midsummer sun. It didn't set. And this was a beautiful night where there wasn't much wind. So the ocean's completely flat. And then there are massive storm systems in Antarctica. So I'm showing you all these like really nice, beautiful pictures with like a flat ocean, but it's more because that's when you can go outside. If it's really rough, they just tell you you cannot go outside. These are little juvenile emperor penguins, so they're about a meter tall. And you can see like this is the Ross Ice Shelf in the back. This was a little bay that had collapsed a few years ago. And you can kind of just see the scale of it. This was closer to land, and this was quite a special place. The Italians had a mooring here. Please don't laugh. They did not get it back. It was very sad. So if you really, really, really want your mooring back and it's covered in sea ice, you can do donuts with your boat and open up a pond and then let it come up, and hopefully your mooring comes up straight and you don't lose your mooring. It's a risky thing, so they generally don't want to do this. But we were sailing through the sea ice, and normally you can kind of see where you've been, but this just closed back in. And also, so this was really close to land, and it was just impressive to see all those glaciers and how much ice there is. So this, yeah, one of the icebergs. I think this is my most pretty picture of the iceberg, so that's why I put it in this presentation. And yeah, then it was time to go back home. We were again further north, 2 months into the year, and we got to see our first sunset, which is pretty spectacular.
Thank you very much, Liv. And I have to say that you've seen some things that I wish I'd seen, so I'm envious as well. Have we got some questions from the room? And also anybody online, please put your questions into the chat.
Given that it was a joint New Zealand-Italian mission, was language an issue at all?
No, so the Italians spoke very good English. I now speak probably 3 words of Italian. Yes. But yeah, luckily the Italians were great with their English and super helpful with, getting out of their way and talking English. Yes. Yeah, no, I've had some bad moments as well. At some point you just really want some proper food, and you just want to go home and get to your loved ones and your pets. but I'm always trying to be positive. So I did smile a lot, I think. Yeah.
Question online. You mentioned you didn't get all the moorings back, unfortunately. Did you still manage to get enough data that you needed for your own research?
Yes, so luckily the moorings that we were trying to recover and redeploy have been in there for 8-9 years. So yeah, I have been able to get all the data for my PhD, and hopefully we get them back next year.
Thank you very much, Liv. That was lovely. Okay, so now I'll hand over to Sydney.
Kia ora koutou. My name is Sydney Dean. I'm a PhD candidate at Te Herenga Waka. My team and I have been investigating whether there are solar-powered bacteria in Antarctica, particularly in the McMurdo Sound. So I would have been existing on the ice that was melted by the time Liv got there, which is really, something to think about. So this is a view of Cape Evans, and we'll get started with solar-powered bacteria. Some of you may or may not know that solar-powered bacteria even exist. They exist because of a protein called rhodopsins. You and I actually have them in our eyes. In our eyes, they help facilitate vision. They're also light stimulated using an opsin protein, and the pigment that they use is retinol. The important point here being that they use retinol, not another pigment we might be familiar with, which is chlorophyll. These are known as type 2. They're in our human bodies. Type 1 refer to microbial rhodopsins, which were discovered only in the 1970s, and they were only discovered in bacteria in 2000. Within microbial rhodopsins, there are a lot of different groups. The group that we're particularly interested in are proteorhodopsins found in proteobacteria initially. Unlike the ones in our eyes, they're a little less complex, and they primarily like to pump a hydrogen atom out of the cell when stimulated by light. Hydrogen does not enjoy being outside of a cell, so it likes to make its way back in, triggering ATP synthesis and providing additional energy to the cell. This is to say that the cell will still like to consume organic material, but it potentially has a way to supplementarily provide for itself. Just a few years after they were discovered, we found that there are some which spectrally tune using one amino acid towards blue light, and some that like green light. You may ask yourself, how does one amino acid make such a massive change, whether they like blue light or green light? And there are lots of people who have asked that question. I am not going to take you through all of these amino acids, rest assured. The point being that glutamine means blue, generally. Leucine means green, generally. However, you also have some friends who have valine at that position, and they are said to be blue. And you also have some who have arginine, and they are not said to be blue or green. What are they? I do not know. So let's carry on. Why are these colors important to us? Unlike the way that we know that light penetrates into the open ocean, where blue light is going to dominate deepest and then followed by green light, in the sea ice column, when we've got about 2 meters of sea ice over the ocean water, we know that blue light is going to dominate a majority of the way down, but then at the bottom we have green light. About 15 years ago, someone took a look at the proteorhodopsins that might exist there, particularly blue and green. They found that blue does exist, but green is definitely dominant all the way through the sea ice column. Very interesting because they don't really have much green light to work off of. This is what it can look like at the bottom. It's gorgeous. This is an image provided by NIWA. Thank you, NIWA. But this is what it can look like through the rest of the sea ice column. There's not a whole heck of a lot there. So this is really to showcase that in that bottom 10 centimeters of 2 meters of ice, that's where we have a lot of biomass living. So algae, bacteria, and it's heavily used by other parts of the ecosystem as well. So I want to talk a little bit about what we did in 2022. Don't get overwhelmed. Everything's okay. We're not going to talk all the way through this, I promise. In 2022, I was new to my PhD, and we did an experiment that was extremely experimental. I lovingly call this experiment my Frankencore experiment because we've Frankensteined a bunch of cores together by drilling a lot of holes, taking the bottom 10 centimeters with all of that really juicy biomass, picking them up and translocating them either to the top, the middle, or the bottom of the sea ice column. We then may have put a color treatment on the top, and I'll talk a little bit more about the colors in a little bit. We put some sensors in and we got down to business. Now in 2022, we could only put them out for 18 days. And by 18 days, I mean the sheets themselves could be out for 10, and then we had to pick them up for the last 8 because it got too warm. That does happen in Antarctica when you're living on the sea ice. This is what I'm looking for, people. This is the bacteria. Isn't it so beautiful? If anyone would like to count bacteria with me, please see me after this presentation. I'm obviously looking for volunteers. But what we found from our very complex study were some very interesting and complex results. Yes, the microbial community has been defined before, but it's not been published, and we thought that it was worth revisiting. The thing that I'd like to focus on is that we did find proteorhodopsin bearing species to be there. So these are the results from 16S analysis, which is basically a way of identifying what bacteria are present. When we look back, though, there can be quite a bit of difference between what we're looking at. It's not just at the species level, it goes all the way back to phylum. This can mean that it's really tricky for us to try to catch things genetically when we start looking at individual genes, because they are present across everything, but they're still very distinct based on their lineage. So that led me down this beautiful rabbit hole. We're going to go through this point by point now. Welcome to this 1-hour lecture. No, I'm just kidding. I fully would not have sat through this lecture either. The point of this is just to show that there is so much difference, and I am going through the specificity of different primers. How do we find this PR gene? Can we find it with one primer? Do we need something for gamma proteobacteria versus proteobacteria generally versus flavobacteria, yada, yada, yada. The point is they're very different. And what we got back is that the ecosystem is dynamic down there. Shocker. So when we went down this year, this is Ross Island, just to orientate us. We started in Scott Base, as most people who got to camp do. And then we made our camp at Cape Evans for 1 month. We were lucky enough to make it up to Cape Royds, which is absolutely gorgeous. I'm happy to share some photos after the presentation if anyone would like to see what Shackleton's hut looks like. And we were able to deploy a 3-month experiment at Turtle Rock, which was our absolute dream and what we were trying to do with our previous 18-day experiment. This is what Turtle Rock looks like towards the end of our season. And this is all snow on the ground, which is absolutely great, meaning that we got some snow blow in and meant that I had a more dynamic experiment that happened. So I was really excited about that. We put these colored sheets down, and they're roughly 5 meter by 5 meter. And that means that when we core from the very middle, we know that we're getting ice on the bottom 2 meters down that has been treated by this color all throughout the 3 months. We don't want to take from the edge because then there's a lot of mix in the light attenuation. That's what they look like when they're fresh. This is what they can look like when they've been out for a while and it's a little bit warm. So things start to get a little bit risky, and we like to pull them before we're a danger to the environment. But this is a lot of mahi that we put in. Because we previously used bottom ice, which is so friendly, so easy to break apart, it's basically slush. You take your vial, you give it a little scrape, you get your bacteria, your algae, everything you need, happy days. Because I wanted to take a step back from the experimental approach, and I wanted to see what happened in the natural community under the different light treatments at the top and middle, which are much denser, much harder ice to work with. I'm going to offend everyone who's a mountaineer or climber here. I used ice screws. It's heartbreaking to put them in salt water. They do rust very quickly, but essentially you can screw straight down into the ice, pop it up, pop that into a tube, the little core that you just took, close it and freeze it. Easy as. It's absolutely perfect, and it's probably the highlight of my PhD. Please give me my degree now. No. I will warn you not to freeze your falcon tubes without testing them first, because sometimes they don't last. So why are we so interested in the bacteria and the algae? There's a complicated relationship around whether bacteria use these rhodopsins under nutrient stress, under salinity stress, under temperature stress, under pH, under light conditions, yada, yada. And there's even a relationship that's been shown between chlorophyll presence and proteorhodopsins particularly, but generally rhodopsins. So we were thinking about some of these complicated things when we chose our colors. We obviously used blue and green because we know that there are the blue and green proteorhodopsins. But we also used red for two reasons. One is that blue and red are generally pretty appreciated by some algae that exist underneath the ice. That's within the chlorophyll A optimal absorption. That's the purple line that you see on the chart. However, when a previous student had studied a PR-bearing bacterial species under different colors, they found that red was actually worse for that species than darkness, complete darkness. So we thought, okay, red could go one of two ways. Red could be great for algae, red could be really bad for bacteria. Not sure. Still not sure. When you're studying microbes in Antarctica, most of your results happen when you're back home, so you're kind of flying blind. This is basically the observations that I had to work off of. So we know the control did pretty well. We didn't do anything to that, so why wouldn't it? Confusingly, the green bottoms tended to have quite a bit of algae. They tended to come through better than the reds and the blues. You might say to yourself, but I thought that they didn't really like green light. Yeah, so did we. And then the reds and the blues just sort of trailed off a lot at the end. So there's a lot to unpack here. The gist of it is that no, I wouldn't expect that coloring on that top green bottom to be like that just because of bacteria. So I don't know what's going on. We're going to figure it out. And this is just a really nice reminder from a clock at Scott Base that you can't always trust things because they're always wrong. So I had two more experiments that I'll quickly talk about. I was able to use a tank from one of our colleagues at the University of Tasmania, which meant that I got to go out and I got to crack the edges off of that Perspex colored acrylic sheets, and I was so happy. My supervisor cried a little, but it was fine. So ideally, this tank would hold cores that are quite large for 36 hours, but it's a prototype, so we didn't quite make it there. At the very least, I've got a 24-hour study to look into the up and down regulation of this proteorhodopsin gene. And one day I'll be able to hopefully carry that into actual protein presence, although I can't really get into protein function based on my experimental design. I'm just happy to know whether they're there and if there's more of them or fewer of them, really. I also was using tritiated leucine, which is a mild radioactive compound. And this is really important because it helps us understand bacterial primary production. It's something that's very important for protein synthesis. So it's giving me a lot of information about whether the bacteria are producing new proteins as we go along. This was great. And at the end, because I was crazy and I thought I had so much time and all of this tritiated leucine left, I decided to run another experiment because I'm a PhD student. That's all we do, really. So I ran this really long experiment throughout the night because essentially the protocol I've been using is from 2001, and I wanted to know, does light, temperature, etc., affect how the leucine is actually uptaken by the bacteria? Is this still a good method for us to be using? And consistency really is key, but if I can find the best way, then there we go. So essentially by the end, I was leaving messages for my supervisor on the whiteboard. And I went to bed with the radio because that was the only time we saw each other. And I ate dinner for breakfast, etc. So that's sort of what we got up to. And this is more of the fun anecdotal part. We've been through the mahi, we'll do the treats. This is what the inside of a wanigan, which is a shipping container set out on the ice, can look like. And this was my lab. I got very comfortable in it. And this is a little bit of a mess because it's at the end of a month-long trip out on the ice. And if you think that I was tired, my equipment also got tired. So my little Eppendorf centrifuge started to give out and give me an error code. So you always keep your alphabet nearby and your calculations nearby in case you need to radio Scott Base and get on the phone and say, could you please Google for me? Echo, Papa, Echo, yada, 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 until you've spelled out Eppendorf, mini, spin, centrifuge. This is the addition, this is the error code. And so 2 hours later, you finally know that it's just because it got too hot. So you have to put it outside and run it in the Antarctic environment, which is fine. So things got really intense and we did calculations about tritiated leucine over the radio, etc. You just, as Liv said, roll with it. I do have a few videos from some of the guests that we saw that I would like to share. So we had some friends from Cape Royds come down, just on their own, doing their thing. I just think it's really cute to watch them run. And of course, because we are explorers out there, we want to make sure that we're getting low and providing the animal with the opportunity to approach us, never approaching the animal itself. He wasn't very fond. I don't know why. We all smelled horrible, so I would have thought that we were just his cup of tea, but he didn't like it. We also went to investigate a dive hole. So this is a very large square that someone else would have been using to deploy equipment. And we were kind of hoping to sneak in and use that same hole because we had some equipment to deploy. But it wasn't meant to be because it was already being inhabited by someone else. And so we got a little bit of a fright from a friend, waited a minute, and poof, there you go. So we pretty quickly backed away from that friend, and we, let them go about their day and decided that we'd just have to drill a new hole. So we had a really exciting time. These are some footprints from an Adelie penguin. And if you would like, hang on. If you would like to see more videos from our 2022 trip, you can look up Out There Learning on YouTube. We had a really lovely videographer named Julian Thompson with us. He made some gorgeous videos about the science and the fun that we had. And I'd just like to say thank you to the organizations that supported us and to NIWA and the Antarctic Society for having me. It was lovely. Thank you.
Thank you so much, Sydney. I saw those coloured sheets out on the ice in 2022. It was the strangest thing I've ever seen in Antarctica. Okay, any questions from the room?
You mentioned the rhodopsin, there's the type 2 and the type 1. So you think that the type 1 was discovered after the type 2?
Yeah, so type 2 refers to the one that's found in eukaryotes. So it's just more complicated. I think it's a G coupled receptor protein, but don't quote me on that. The point is that the more simplified type 1 encompasses all microbial rhodopsins. So that includes the proteorhodopsin that I was talking about, but it also includes microbial rhodopsins in yeast, fungi, bacteria, et cetera, that behave a little bit differently from the proteorhodopsin. So they're just the two different types that have been defined. And that might be because of the way that they came to exist. I'd have to double check on the whole type 1, type 2 thing. But yeah, there is the type 2 that you and I have, and then type 1 is the microbial rhodopsin. Very interesting distinction there. Yeah. Thanks so much, everyone.
Thank you so much, Sydney.
Okay, hi, I'm Craig Stewart. I'm an oceanographer here at NIWA, and a little bit crossover into glaciology from time to time, as you're going to see. So I was out in November and December on the Ross Ice Shelf, and this is an ongoing project, which is a master and fast half mine, and working in conjunction with a few other people, with Mike Williams, Keith Nichols from British Antarctic Survey, and Wolfgang Rack as well. So before we get too far, what are ice shelves? Ice shelves are, well, you can see in the picture on the right there on the screen, the light coloured areas. They're where the Antarctic ice sheet comes afloat because it's become too thin near the edges. Ocean gets underneath, and they're basically where glaciers flow together, spread out on top of the ocean. And that's a picture on the left of the front of the Ross Ice Shelf. They fringe much of Antarctica. The Ross Ice Shelf itself is twice the area of New Zealand, so it's about 500,000 square kilometres. And underneath it is a cavity full of seawater, and that exposure to the seawater is really what links the Antarctic ice sheet to the oceans. This here is if you took a slice through the side of an ice shelf, and it shows where mass comes from and goes to in an ice shelf. On the left, you can see ice flowing out from the grounded ice sheet into the ice shelf. On the top, you have snowfall accumulating. So those are both adding to the mass of the ice shelf. And the processes that kind of eat away at the ice shelf are basal melting from the ocean below and iceberg calving at the front. So why are we interested in ice shelves? Well, unless you really haven't been paying attention, you probably already know that Antarctica, the Antarctic ice sheet is losing mass. It's wasting away in certain areas, and the red line there is the mass loss from the West Antarctic ice sheet, and the blue, I'm pretty sure, is the East Antarctic ice sheet. So there's two quite different catchment areas and two quite different stories with accelerating mass loss from the West Antarctic ice sheet. So we've got to think, why is this happening? And if you look at satellite estimates of changes in surface elevation, this picture on the right there shows that the mass loss from Antarctica isn't evenly spread over the continent at all. It's really focused in particular catchments. The blue area is the CAM, which is the only region that's really thickening because it froze onto the bed of the onto the sediment below, probably 100 or 150 years ago. But the areas are in red are where the surface is lowering. And I don't show it here, but if you follow that through to the ocean, you can actually see that pretty much all of those areas where there's dark red colors are upstream of where you have ice shelves that have been melted from below by warm water, which has managed to get into contact. So if you compare that map there with a map of seafloor ocean temperature, they match really well. And it's a really telling thing that tells us that large-scale changes in Antarctica today are being driven by the ocean. So we're going to zoom in now to the study area, and this is the Ross Ice Shelf. On the right there is an estimate from satellite altimetry of the melt rate. So you can, by sequentially taking measurements with laser or radar of the surface height, in conjunction with measurements of the speed of the flow, knowing that it's floating, you can make an estimate over the long term on the melt rates. And on average, melt rates under the Ross Ice Shelf are very low, probably about 20 centimeters or so if you were to average across the entire 20 centimeters per year, that is, which is similar to the amount of snow falling on the top of the ice shelf. And the reason for that is because it's at the back end of a very large, shallow continental shelf where cooling of the ocean during winter makes a large, cool body of water. And so the water underneath the ice shelf is very, very close to the surface freezing point. So even when it's in contact with the ice melts very, very slowly. The exception to that slow melting is really concentrated in the bottom right of the image there, which conveniently for us is right beside Scott Base. Sorry, I haven't orientated you there, but north is actually down the page. And so, can I get a cursor on there? Yeah, so this is Ross Island there, the Scott Base right there. And this area here is an area, well, it's other than the Bird Glacier, which has very high melt rates because it's so thick. This area has high melt rates and was the area that I studied during my PhD. So if we zoom into ground-based observations, this is a map of melt rate measurements that I did during my PhD, and they confirm that rapid melting within that band just east of Ross Island there, and especially near the ice front. And these measurements suggested that this rapid melting may be driven by a mechanism that wasn't one that had been thought about so much before, and that is the introduction of warm surface water during summer. The paradigm being that, well, it might be best to skip to the next slide, but if you look back to the slice through the side of the ice shelf there and look at the different water masses that can get in, typically you can break down melting based on the characteristics of the water that's driving it. So in an ice shelf like the Ross Ice Shelf, a lot of the circulation under the ice shelf is traditionally thought to be due to the formation of a very dense cold water mass called high salinity shelf water, forms as sea ice is produced, as Liv was mentioning, as it sinks down to the sea floor because it's very, very dense and salty and cold, can then flow into the base and cause some melting and come back up. In areas like Pine Island, where the very rapid melting is happening, that's related to this water mass called circumpolar deep water, you can see there with the green arrows, and that is in areas where they can get access into the ice shelf cavities. It's causing very rapid melting because it's quite warm. But a less thought about water mass, and the one that I believe is doing the melting near Ross Island, is Antarctic surface water, which can be heated up during summer by the sun. For the same reason that the sea ice is blown away, you can get a warm surface pool of water. And I guess that's what we're sort of thinking that is causing the melting near Ross Island. So you know, where does that leave us? Satellite estimates are great for providing a sort of global context for basal melting, but they don't give you very good information about the timing of that melting, even whether it's summer or winter. And so what we wanted to do was measure, find out basically when is this rapid melting happening in that area, and further, if we can get a number of instruments that can measure melting, could we track the movement of that water underneath the shelf? So that brings us to the AP-RES instrument. This is a custom-built ground-penetrating radar specifically designed for measuring the thickness of ice shelves. It's developed at the British Antarctic Survey and University College London, and it transmits pulse of electromagnetic radiation down through the ice, which is actually quite transparent to radio waves. I believe this was first discovered in Greenland during World War II, as the bombers flew over it and saw that the ground was about 4K down, but they could see the ice surface rather closer to them. So they, you know, realized that they were seeing right through the ice sheet at the time. So the way it works is that radio waves transmitted down reflects off the seawater interface, the ice seawater interface, and comes back. And using the precise timing of when that reflection comes back, you can see both the ice base, but you can also see internal layers within the ice shelf. So this graph here is a graph from the surface down to the ice base there. And you can see all the way through the ice shelf, there's layers which are quite identifiable because these two profiles were measured a year apart. So you can see there's got this real signature of what the ice shelf is like there. And by using that to cross-reference, you can remove any changes that are caused by compaction in the snow or accumulation at the surface. And then you can look at the difference in the range to the basal refractor. And in this case, you can see that these are from 10 years ago. The ice base moved up some distance between the two observations. So that's the instrument. What did we do with them? Well, we ended up with 12 instruments. NIWA bought 8, and we were loaned a further 4 instruments, and we deployed them out across this area that we believed was melting rapidly. So these were put in a couple of years ago now. We flew out and had a central camp, deployed a number of instruments by Skidoo from there, and the remainder while driving from Scott Base or by flying out for the day. This is what a site installation looks like. You actually bury both the instrument and the 2 antennas. Just keeps it out of trouble with wind moving parts around and things like that. And there's one mast that stands up with Iridium and GPS antennas on that can send you little housekeeping messages to tell you whether the instrument's operating or not. So it turns out there's quite a lot of digging involved in this operation. These are basically a data summary of the first 2 years of operation, and red lines equal good. The instrument was operating, and unfortunately, you can see quite a few dropouts there. There's an instrument issue with the firmware on the instrument during the first deployment, which unfortunately meant that a number of the instruments failed. So we were able to get some repaired in the 22-23 season, and the remainder of which I was out there this season to repair and restart the instruments and upgrade the firmware. So that's pretty much what we're up to. So you can see that looks somewhat different to what we left, chiefly because there's about 1.5 meters extra snow there. And so servicing involved, this was arriving at a site, Ollie Twig, who was helping me this season, progressively getting deeper into the snowfield. It's better if you have a bunch of people. Wasn't always possible. In fact, the way we worked this season, instead of having a field camp, we're actually based at Scott Base. It was my first of many trips to actually be based at Scott Base and just doing day trips out, but it worked quite well. It's quite a lot of snow to move. And that previous one was a very nice day. This was actually much worse conditions than it's like on the video. We were near Cape Crozier and the wind was steady 20, 25 and getting up to 30 knots. So we're on the border of what the helicopter was. It didn't look like that at all there, but I can assure you it was. The helicopter was only just happy to hang in there waiting for us to service that site. On the upside, there was a very little accumulation because all the snow is just blown away immediately. Redeployment, it's actually easier just to dig new holes for them than to try and put them back in the mess that you end up with. So we were servicing the instruments, putting in new batteries, upgrading firmware, and that sort of stuff. So I don't have much to show you in the way of results. It's really just a sort of telling you where the project is at the moment, but these are some very briefly, if we look at site 1, which is right near the ice frontier and in the center of the line where we think the warm water is blowing into the ice shelf, you can see that when it was deployed in 2021, the ice base is here at about 106 meters or something, and you can see that the internal layers are matching reasonably well. This hasn't been done perfectly, but you've got a significant amount of melting or thinning, I guess. I haven't accounted for the deformation of the ice and so far in this analysis, but there's a clear change there of probably 6 meters of ice lost off the bottom of that one. Now that's just from a first and a last shot. But of course, the point of leaving the radars at the site is that they'll take a shot every hour. And so we can also look at a time series of the range to the bottom. And that's this red line here with the range to the base in meters there. And you can see that essentially what we're seeing is a dropout there during winter. But basically, you've got this slow melting throughout winter and then really quite rapid melting. And I guess in some ways, that's what we expected to see if we believe that that melting is driven by the warm surface water coming in during summer. There's a step there that's an artifact of when we actually serviced it. So I've got further processing to do. This is just really early days on this, but it looks from this like this year was actually a pretty big melt year for that area. And that would make sense because there was very little sea ice. And with this type of melting, it's unfortunate, but quite interesting, very rapid loss of sea ice at the moment around Antarctica would change this, would make more heat available for this sort of melting because you'd have more heat being absorbed in the top layers. So where are we at the moment? We've got, we've got 12 operational instruments. This is the network as of 2 o'clock this afternoon. Lots of green things here. I can get the status of it. I can get very small data snippets, but not really enough to get an accurate melt rate. And we are going on for another year, and hopefully we can get a relatively clean record with most of the instruments operating through the following winter. That's about it for the science. Just a huge thank you to everyone involved in the project. It's been a lot of work. Marsden Fund and Antarctic Science Platform for the Sport, NIWA, Antarctica New Zealand, and all the people, Ollie Twig, Scott Barry, Andrew Sussex, Hugh Tran, and very many others who dug snow with me. And just before I finish up, we're not too late. A couple of videos. There was quite a lot of digging, but the occasional high point, which were usually associated with getting to the sites or back. So this is the helicopter back from one of the sites out on the middle of the ice shelf. That's what the installation looks like now. It'll look a little bit tidier now. And that's looking back towards Mount Terror. and Cape Crozier is just up there. Most of the bamboos are just marking corners of things that we're going to need to dig up next time. And then the mast has a small solar panel, which is recharging the batteries. So we're flying off back towards Scott Base. You're just starting to see the ocean there, Beaufort Island in the distance. And in fact, we just, with Liv, we were just in the icebreaker along this very front of the ice shelf, 6 weeks ago, I guess. And we deployed 4 moorings in the front there. So we'll hopefully be able to look at which way the ocean currents were going and understand more about what's bringing warm water into the cavity. Further on the way home, Kath, the pilot, very kindly decided to show us some of the glaciers on the south slope of Mount Terror, and it was pretty amazing. So up on the right is Mount Erebus, down on the left is Windless Bight, and right at the end of Hut Point you can see is where Scott Base is, so we're just heading home. But one thing you don't quite get in this particular snip of the video is the size of those crevasses, but when you see the shadow of the helicopter, I mean, you could just fly the helicopter right into some of them. They're that big. It's absolutely amazing. So the ice sheet flows down here, goes starts to float about here. So this is all the Windless Bight area of McMurdo ice shelf, and this is the final part of the ride. Just coming back in, we're just on the very edge of. Oh, you can see a car driving along into towards Scott Base is here on the end of the peninsula. In the front, there's this is just the thinnest bit of the ice shelf. You can just about make out the transition onto the sea ice there, and these pressure ridges here, where the ice shelf is buckling under the compression against the coast. Now there's a change to sea ice here, and these are the pressure ridges in the sea ice where it's been pushed until it buckles. And we're just coming into. See Scott Base there, all the green buildings and plenty of containers parked out the back. This was my last day in Antarctica. I was scheduled to fly home the next day, so I was checking in to weigh my bags that night, and I was feeling very, very fortunate to have been able to get to all of my sites because I was going home regardless at that time, and we were just super lucky to manage to get the work done. That's it.
That's absolutely wonderful. Thank you, Craig. Such a lovely data set. I'm really looking forward to seeing both sides of the data come in. Have we got some questions for Craig?
What sort of things cause instruments to fail? Just degrading over time, water damage? Or...
In that particular instance, it was a firmware error, so it was basically just unfortunate. They're produced in quite small numbers, and due to the error, they started recording double the data rate and filled their cards. And so, and once they filled their cards, they stopped. So it was unfortunate. I mean, it's also fairly challenging conditions. The other thing that would usually be the main cause of problems is battery failure. The instruments are rated to, all the components in them are rated to -40, and so the SD cards that we use in them. But basically we're using lead acid batteries, and they're really struggling once they get to -40, and we were getting to that in winter. We're getting to that -40, even 45 for a little while in winter, and that's just the margins of what rechargeable batteries can really deal with. You can use other batteries like lithium primary batteries, but they're non-rechargeable and they're very, very expensive. So I mean, it's not so much the expense, but the fact that you can recharge the lead acids is really nice, because if you if they can make it through, then they're good again for another year.
How exactly was the rate of sea ice measured by the radar? Were you comparing the thickness of ice at 2 points, or?
Sorry, I might not have explained it too well. Each instrument is left buried within the ice shelf. So it's measuring the thickness of that particular bit of the ice shelf, and the instrument, even though the ice shelf is flowing towards the sea, in fact, most of our sites were moving 2.5 meters a day seaward, but the radar itself is moving with the ice. It's continuously measuring the same column of ice rather than the same geographic coordinates. So you're measuring a different thing. If you wanted to measure the change in Antarctica, you're better off doing a satellite measurement at the same point in space, but that conflates a number of different things, because when you have thicker ice flowing down from upstream, it also measures those changes. What we're trying to measure is the direct influence of the ocean on the ice shelf, and doing that with the instrument measuring the same column of ice gets more directly at the ocean melting component.
Out the thickness of that particular.
Yes, sorry, yes, yeah. It's just repeated measurements of the thickness of the ice, but in a very precise way. So when the radar, the carrier wave that goes down and hits the base reflects back, and the precise timing of the reflected wave is measured compared to the transmitted wave, the relative phase of those two waves. And that can give, it's like a kind of a vernier scale on your range measurement. So you can measure very small changes of, well, in theory, less than a millimeter, but it can be impacted by other things. Yeah.
Great, thank you, Craig. And our last speaker tonight, Liz Keller, who's at GNS.
Right, thank you. Good evening. I'm Liz Keller. I'm from GNS Science in Victoria University of Wellington. And I'm going to tell you about our most recent season at Discovery Deep. I had an absolutely awesome team from left to right in the photo: Andrew, Charlotte, Oben, Hamish, and myself. I'm going to tell you a little bit about the science as well as our daily life out on the ice. This is my first time in Antarctica. Had an absolutely great time. I'm a modeler. They don't usually let me out of the office. So I'm very excited to share this with you. So why did we go to Discovery Deep? It's over here on the western edge of the Ross Ice Shelf. It's just on the other side of the mountains from Scott Base. It's thought to be one of the deepest areas of the Ross Ice Shelf ocean cavity, and it's been flagged as a potential location to drill for a sediment core and obtain a paleoclimate record of past climate. And the particular shape of the basin means that the sediment layers might be the thickest and contain a really nice high-resolution record of past climate. So our goal in this season was to collect geophysical data, both seismic and gravity, image the subsurface, to characterize the site, and find the deepest point underneath the ice shelf. This is a gravity model of the seafloor depth. Blue is deep and red is shallow. So you can see this is where Discovery Deep is. It should be where the model indicates is the deepest underneath the ice shelf. This is a zoom in of that. So this was our polygon of safety where we are allowed to operate safely this year. This yellow line here, that is previous season, 2021-22, where they did a seismic line. This year we concentrated on the western edge here. We extended line 1 out to the west. We did a line perpendicular, line 2, and we started a parallel line, line 3. So I'll explain how seismic data works. First of all, you need a sound source, which in our case was explosives, which I'll show you a little bit later. But the idea is that the sound waves travel from the surface through the ice shelf and the ocean cavity to the seafloor and the sediment layers underneath. They bounce back up and reflect, and we have an array of sensors at the surface to detect that reflection and form an image of the sediments and calculate the distance from the surface to the seafloor. This is what the gear looks like. So our sensors are called geophones. They're these metal cylinders that you see in the picture on the right. Laid out here at Scott Base, there's about 300 meters of wire, and they're connected, separated by a few meters, and they're laid out on the surface and towed behind a skidoo. So this is the dog box. It's called dog box because it's on one of those old style dog sleds with the dogs used to pull. It contains a computer and batteries that control the whole operation, and it collects and stores the data. And it's also towed behind a skidoo. And you also, if you look closely, you'll see this big red button that triggers the explosion. And the final piece in our setup is the explosives. So this is a detonating cord. It comes in these big reels. It's basically plastic tubing with white powder inside. And then we have a metal piece that goes on the end. That's what creates the spark to light the explosions. So I'll go through all the steps involved in laying out a shot. So first we lay out the detonator cord. We measure out 10 meters of cord. And then someone tapes up the detonator to the end. We bury the cord in a shallow layer of snow just to contain the explosion and encourage the sound waves to travel downwards. And from the detonator, there's a wire that comes out. And there's someone in the middle who's connecting up the wire to the wire that goes out to the dog box. And then someone connects the wires to the trigger box and presses the big red button. So I will show you what that looks like. This is Charlotte connecting up the wires. There it goes. So we stay quiet and we stay still for a couple of seconds afterwards, just because the geophones are really sensitive and they pick up any movement on the snow. And then we're free to move. That's what it looks like from the side on. It's very fun to watch. And then we're ready to move up the gear 60 meters and start all over again. Charlotte driving up the dog box and the geophones.
Charlotte going the dog box, going up 60 meters to the next shot and standing on the side of the last shot.
After it's exploded.
And Charlotte will stop right about now. You can see the geophones all coming into place. I'm basically ready to record the next shot as soon as Hamish is wired up. And I have connected the trigger to the dog box.
Now we start all over again. The other piece of data that we collected in the field was gravity. So the photo on the left is the GNS gravity meter. It contains a spring that's really sensitive to differences in mass and density in what's below the surface. So we put that on the surface, we make sure it's level. We turn it on for about 2 minutes and let it record data. And that gives us a relative reading of the density that's below the surface. It's a relative measurement, so we need to calibrate it against known sites. And luckily there are some around Scott Base. So before we left for the field, we spent a day doing gravity measurements at these sites so that we were able to calibrate our measurements that we made in the field. And we made these measurements along all of our seismic lines every 600 meters, which is about 10 shots, so that we would have both a check on the seismic data and an independent data source. Okay, so now I'm just going to take you on our journey and tell you what our life was like. So we started in Christchurch. We boarded a Hercules owned by the New Zealand Air Force. See, it's quite cozy inside. Makes commercial airline seem like luxury, but we do get a gorgeous view of the sea ice out the window going south. So we spent a few days, or about a week and a half at Scott Base preparing to go into the field. Some pictures didn't show up, that's okay. So we did things like skidoo training. We spent a night camping on the ice to prepare for the field. We sorted out logistics, we packed up our food, and we also got out and about for some walks around the base. And then when it was time to go into the field, they were flying. And then the rest of us followed by plane by Twin Otter a few days later. So get a gorgeous view of the mountains going over to the Ross Ice Shelf. This is what our camp looked like. So we had our toilet tent, we had our fuel station, which fueled both the skidoos and the generator, and our stove. We had Polar Haven, which was our communal tent where we did all of our cooking and hung out at night. We each had our own sleeping tents, and we had 4 skidoos out with us to help with the work. This is what it looks like inside our Polar Haven. You'll notice we had a disco ball. This is where we did all our cooking. We had a stove that was on all the time, and it even got up to a nice tropical 25 degrees on occasion. And we had an oven where we could do some baking. So these are our sleeping tents. We had 2 different styles. We had the more modern polar domes and the traditional Scott Polar, the triangular shape. I was in one of the Scott Polars, and I'd add that it was actually surprisingly comfortable and warm. All right, so I'll take you through a typical day out on the ice. We had a nice leisurely breakfast from 6:30 to 9. Coffee and tea was available for self-service. It looked more like the left than the right. The right is actually Scott Base, but you get the idea. 7:30, we had a check-in with Scott Base just to get a weather report, an update on our daily activities, and any messages that we needed to pass between us. We did have an old style radio, but we also had Starlink in the field, so we were very well connected. Then around 9:30 or 10, we would get on our skidoos and commute to work and get out to our line. And then we'd work for about an hour and a half, take a break, do some more work, break, and on like that until 5 o'clock. When we did our last shot, we were fairly strict about that because we didn't want to get tired and make mistakes at the end of the day. So at 5 o'clock, we packed up, went back to camp for dinner. We took turns cooking, a little bit of data processing, and maybe some movies as well. We didn't work all the time. We also spent Christmas Day out in the fields. It was snowing. We had a Christmas tree. We had stockings by the fire. And Santa did come and he baked cinnamon rolls. It's pretty cool. So I mentioned at the beginning that we were looking for the deepest point below the ice shelf. So this data is from the first season. It's 2021-22. You can see it's steadily sloping downwards here to the west. There's this sort of tantalizing glimpse here that it might be leveling out. So the first thing that we did when we got into the field was we extended this line out west to see if that really was the bottom. It wasn't. It kept going downwards, sadly, to the end of our line. I don't have the data to show you because it's a honors thesis still in progress. But anyway, just means that we might have to come back. So one last shot before we go. This is our last day in the field.
Woohoo! That's a wrap. What a day.
Best weather we had all season.
Give me a thumbs up, Charlotte.
And that's the end. Thanks to Antarctica New Zealand and the staff at Scott Base for their support.
Have we got any questions for Liz? Down the back.
So, how many days were you out on the ice, and were there any days where it was too bad, the weather was too bad to actually go out?
Yeah, so we were there for 3 weeks, shorter than planned, unfortunately. There were a few days when it was marginal. We don't want to go out when it's really windy because that creates a lot of noise in the data. And it was snowing on occasion as well, not great conditions. So there were a few days when we just took the day off because, yeah, the conditions weren't all that pleasant.
What were you saying when we couldn't hear you because of the helicopter?
There were 3 of us who went into the field in advance to set up camp. and 2 of us stayed behind and followed a few days later.
What is it like to sleep in those tents? Because we'll just try and sleep in Antarctica in general, because the sun doesn't set.
Yeah.
So is it difficult, or do you get used to it?
I wouldn't say you get used to it, but I mean, it's like camping anywhere. You've got your sleeping bag, it's nice and warm. I guess you wear an eye mask. That's what I did, just to block out the light. Yeah, and I guess you're just so tired at the end of the day, you just fall asleep.
Oh, a question from online. So cool, Liz. What difference did Starlink make?
I think, yeah, it was really nice being able to stay in touch with home, with family. Definitely was a morale booster, I think. Yeah, just being able to stay in touch was great.
That must be close to Scott Base, though.
Yeah, so that on the left, that's Nigel. He was hanging out.
Okay. As a member or lead, I suppose, on the outreach committee for the Antarctic Society, we're just encouraging people who have Antarctic experiences that they'd like a platform to share those on, offering an opportunity, or rather soliciting content that we can share with you via our social media channels. So we've got Facebook and Twitter. We'll get Insta shortly. Our Radio Scared regular newsletter, and also potentially our flagship Antarctic magazine. So if we know that there's lots of stories going back many years, potentially right here in this room, and lots of interesting things that people might be willing to share with the world via our platforms. So do get in touch with me if you are interested, or I've put a Dropbox there at the QR code. So thank you all very much for coming, and thanks to those online. And please just join me in thanking all the speakers for a really lovely session.